start at the beginning. The wings of the butterfly are divided into various segments, as Joel showed in one of his slides. And the point of this talk is to look at what's different within each one of these segments and see how the history of ejection may have changed over the course of years, or at least how it differs from one segment to another. These are the people that are in our group, and they're fantastic. We'll start here, although Joel pretty much went through a lot of this material before. What I really want to point out is that if you step back and take a wide field image, there are lobes popping out of this nebula way out here, and I'll say a little bit more about them in a moment. Joel pointed out the temperature of the star is on the order of 200,000 degrees, so it's definitely not a symbiotic central star. It's a really massive one. And from our estimates of the luminosity and the temperature, you go to an HR diagram and you pull out Miller-Bertolami's evolutionary tracks. The central star is about 3 solar masses, and the time after which the star reached 7,000 degrees is a mere 600 to 1,000 years. That is really interesting. It's a very dynamic nebula. And as I point out down here, is this really a butterfly or a butterzilla? This thing is a monster. Now, studying monsters is interesting, but only if they reveal certain things about the nature of planetary evolution that you can't get from more ordinary objects. And certainly, we see that evidence right here in the wings of iron 2. Right, so here's a black and white image of that. There are little tendrils of iron 2 even out in here. My suspicion is that that's mostly selection effect. The iron 2 line is excited only at densities above 10 to the 5th degrees. I forget the name of the reference for that offhand, but it's a very, very powerful argument. So we are looking at really dense gas, which is being slammed. That iron 2 line is common in supernova remnants and Herbig-Haro objects, but not in nearly all planetary nebulae. Now, I can't do it. This shows the N2 to S2 ratio. If we were looking at ionization fronts, those lines would be pretty much the same throughout the ionization front. The sulfur 2 would come from maybe a little further away from the star than the nitrogen. But there's just a mess of smooth, high nitrogen emission from out in here. And that's related, I think, mostly to the nitrogen abundances. But it serves as a warning flag that there may be more to this nebula than photoionization. We already know that from the iron 2. And it's true here. And we'll come back and look at that again. Before we do that, though, let me put the iron 2 image on the wide field image and point out that the iron 2 looks as if it wants to creep up into this edge of the northwest breakout. And there's a little bit of a hint of another breakout lobe down in here, although deeper images would really be needed to show that. It's interesting that the flow into this large lobe is along one edge, as if the flow somehow thermalizes and creates a balloon that expands outward. And in support of that notion are the long slitted shell spectra shown down here. There are only 2 slits. We only have, amazingly, for this nebula, there are only 2 slits that have ever been placed down on the nebula and the results published, as far as I can tell. And they're both right here. Slit B goes through this breakout up in here, and look at the width of those lines. I mean, lobes expand. This is a lateral expansion that we're seeing, sideways expansion, and it's about 120 to 150 kilometers per second. Lateral expansion comes from thermal pressure. So getting that sort of a width requires that this thing be filled with very hot gas. Now, we all know that ordinary planetaries that are closed often show soft X-rays. And I don't think anybody's ever looked at this. My guess would be that the emission measure of X-rays would make it undetectable. But anyway, there's a lot of energy out in here, a lot of energy. Now we're going to look at some line ratio images, two of them. The first of them is O3 to H beta. The value of line ratio images is that reddening disappears if you pick the lines right, and you sort of normalize one line to the brightness of the next. And when you do that, all kinds of subtle features show up. And it was this image that led to the proposal that the structure of this is wedge-like. There are two obvious wedges right here along the iron 2. The O3 goes dark at the edges of the clumps in here, as you might expect. There's quite a bit of it in this region. But what caught my eye when I first looked at this are features like this, where the O3 to H beta ratio lies along the edge of something. In photoionization, the photons stream out radially. You don't get many instances of radial features other than filaments, and this just doesn't look like a filament in which you see that sort of behavior. So I became suspicious that we were looking at a region of very hot gas in here, powered by winds coming out of the central star, but maybe not at the same speed in all directions. Now, next we go to the N2 to H alpha ratio image. The lines here, the wedges are the same ones. I love this gap. It points right into the breakout lobe in the northwest. That and this both join that breakout lobe that we saw earlier, here and there. And something, I think the fact that there are no clumps in here and maybe not much going on over in there, that suggests that this is a region of flow where, and I can't explain this, a lot of energy is working its way outward into those lobes. There are amorphous regions where there's no bright structure at all, and then there are the very conspicuous clump zones. All of this points to a very complicated history for the formation of the lobes, and maybe not just a single outburst event, but several of them. Now that takes us to the proper motion studies, which are just getting underway. An undergraduate and I are just beginning to do this in careful detail. But in the sulfur 2 to H alpha, the sulfur 2 proper motion study, this is a difference image that Joel made. The expansion rate is about 5.5% per millennium. So that's, 1,800 years. But this pattern of motion, while it's shared in some zones, isn't shared here. Now the sulfur 2 line is weak, and I don't want to say too much more about the proper motion studies until we get into the images that are far brighter. The big advantage of sulfur 2 is that the features in the clumps are very sharp, and you need that to do proper motion studies, but there's more to be learned in here. And as you can see from the black-white differences, there may be some real departures from radial motions, but more about that to come in the future. So what's going on here? Gosh, I wish I could animate this. I guess hang on.
Maybe if you go, into slide, you mean if your slideshow is working?
Say again?
Your slideshow.
I was having trouble with
okay.
Screen sharing. So let me do a preview here. Whoops, yeah, there it is. That's the paradigm. Here's an evil spirit down at the center with a flamethrower swerving around on a turntable. That suggests what is going on here. But as I said, each wedge is so different in character from all the others that they may have different evolution histories, but as best we can tell so far, there's much more to be written on this, they share very similar expansion ages. And that's really interesting. We'll find out more about that a little bit later. So here is the ejection timeline, the central torus in the center, about which I said nothing. Thank you, Miguel, for this image right here. This shows a disk with little feathers hanging out of it, which represents the structure of the CO in the center. The blobs that we see out in the wings come a bit later. Their expansion ages place them at about maybe 4,000 years after the central ring. The shocked central bubble that I haven't talked much about has about the same age as the clumps, right? And this precessing wind here, who knows? I probably shouldn't have put this in here because I don't know how to estimate. It may be a continuing process, in which case there's no characteristic age associated with it other than its beginning. Now, I want to emphasize the point that we have NGC 6302 is a representative of a set of planetary nebulae with really hot and very massive central stars. These guys are all brutes, and so the genus Butterfly Brutus applies to all of them. Now, just to end the talk, when you compare the morphologies of these things, they're big, dense-like structures. And you compare that to the delicate bipolar planetaries, all of which are hollow and that are associated with symbiotic binaries, right? Very hollow lobes, unlike these. These things are filled with knots and junk. These are not. And so I think the paradigm that explains this family of bipolars is likely to be entirely different than that one. I must emphasize symbiotic planetaries have very cool central stars. We're seeing the light is dominated by an AGB companion. As far as I know, no ultraviolet light is found, but the ionization is coming from something, so everybody says there's an orbiting white dwarf, which sounds awfully reasonable to me. So we may have to look at different paradigms altogether for these two types of bipolars. And in fact, there's a question, at least in this case, where the ionization structure is reversed, and I refer you to my poster, which I'll talk about soon. This may not fulfill the definition of a planetary nebula. Quentin Parker and David Frew made a definition of a planetary that says photoionization, and there's no way that photoionization is going to explain why the O3 is further from the central star than the nitrogen 2. But the rest of these things can be reconciled with photoionization, and yet, in fact, you can't rule out some shock ionization. There's a little bit right along the symmetry axis here that was found, some sulfur 2 that was found by Raghvendra many, many years ago in an otherwise, in a nebula otherwise dominated by reflection nebulosity. So I think I want to end there. And if you want to ask questions about particular slides, here's the matrix, and let's go for it. I'm done.
Okay, thank you very much, Bruce. So do we have questions? Just check it. Okay, we have one from Ravindra. Please go ahead.
Bruce, can you go to the slide which shows the N2 to H alpha ratio, please?
Yeah, hang on one moment, Raghvendra. Sorry, but the Zoom screen has wandered away from where I can't see it. Ask it again.
The N2 to H alpha ratio.
Yes.
Can you display that, please?
Sure. Let's put that. Nope, this one.
Yeah, so I'm not sure if there's significance to it or not, but the way you've drawn the gap on the western side, those lines don't go towards the center, whereas for the other wedges, the lines go towards the center, more or less towards the central star. Is there any significance to that or not?
No, this is where my eyes said the clump region ends. It's not, the orientation of these lines is defined by where my eye thinks zones are separated, not necessarily where the direction of wind flow. On the other hand, it's quite clear that there's a lot of wind going on in here, creating all of these tails, especially this one right in here. Let me make that bigger. I can't. These tails all point away, and they're the sort of tails that say that the wind is blowing hard. So there's ablation and probably a lot of shocking going on at the heads of the clumps.
Cool, thank you.
Okay, Martin?
Bruce, impressive talk. We have several papers on the hydrogen-2 molecular content of bipolar planetary nebulae. And we also find that depending on their morphology, they have very different hydrogen-2 content. So I definitely agree with you that there are different families of bipolar or butterfly planetary nebulae. So it's not one single box.
And in this case, I didn't show it, but there is a molecular hydrogen image by Davies from, I think, 2004, which shows loads of molecular hydrogen, mostly very closely associated with these bright streamers here, which is exactly what you'd expect. There is none in the iron 2 region.
Okay, thank you.
Okay, we have a question from Joel. Please go ahead.
Well, just follow up on what Martine and Bruce were just talking about. I have a little bit of PTSD when I mention this, but we proposed to use JWST to get iron 2, which we could do again with JWST at higher resolution, and molecular hydrogen, and we're turned down. So we will keep trying because I really think that's a great way to understand exactly where the shocks lie at different energies and so on. And we expect to see, you know, all these structures that are lighting up in nitrogen so brightly, I think should be bright in molecular hydrogen as well.
As an addendum, what Joel just said, what am I looking for here? The CO has only been mapped in this innermost zone right here. It's mapped with ALMA. The images are great. Miguel's images are just spectacular. But the outer regions here were just too far away to be included in the CO mapping.
Well, fingers crossed. If we get our priority C mapping, then we'll see what CO looks like through the whole field of view of wide field camera 3.
Okay, Albert.
Yes, it is a wonderful object, Bruce, and it's very hard to make sense out of the whole thing, but you've done a very good attempt at it. But I was wondering, this is quite a young object. It may be 5 solar masses, progenitor mass or more, and so it has evolved of the stellar origin quite fast. And I was wondering whether some of the structure we see is due to leftover material from earlier, molecular cloud material that predates the planetary nebula. There is a lot of messy structure around that looks like interacting with other material, molecular material. There's a blob a couple of minutes to the right in your image. Clearly, there is something hiding there. So I'm not convinced it's all ejected by the central star of 6302. I was wondering how much has been left over.
Well, let me get to the right mosaic. These Brutus butterflies have a lot of complex structure all the way through the lobes, everywhere. And although we don't have kinematic information about these clumps, I think the smart money would bet on there being a part of having originated in the central star. It's the nitrogen abundances, which in the case of NGC 6302, say very definitively that some massive central, the gas out here got there by coming from a very metal-rich and therefore very massive central star.
Yes, I agree. The nitrogen abundance shows that it's an evolved high-mass object, but we don't know whether the nitrogen abundance is high in the non-ionized medium. We only know that's high in the ionized medium.
That's right. That's right.
Just a quick comment on Albert's idea that the material could have come from basically the pre-main sequence phase. I gather, right? The molecular cloud that was pre-existing. So I actually floated a similar kind of idea for OH231.8. And then I no longer believe it, because I think that the evolutionary timescales are such that these objects have wandered far from their birthplaces at this point. So I think everything we're seeing, like Bruce says, comes from the central star.
Let me add to that, Albert, that dynamically, the proper motion images, although they're still in an embryonic state of preparation, all show that these knots are wandering away from a common center point. So they came from here. They're not being pushed by winds. They're too massive for that. They got here by moving outward.
Okay, thanks, Bruce.
All right, thank you. So, Martin, I think that we're going to take a break now. So we are a bit delayed, but this is APN, so we have plenty of discussions. And we come back at 10 minutes?
Yeah, perfect.
Perfect. Okay, so see you in 10 minutes.